All right, physicists, I had to go teach this class, and so this is a new video because I don't understand how to use the video editing software. Okay, so you've watched a little YouTube video. Now, let's talk our way through this. So, just to recap, what have we learned? We learned that we have some kinetic energy that's based on the mass of an object and its speed. And so this has units of kilograms times meters squared over seconds squared. And we call that a joule, after James Prescott Joule. And so far we haven't really given any reason why we're doing this so far. We're just trying to map our motion to some number. Okay, so this is just some dumb number, and we'll find a use for it later. Okay, this is a little bit of a silly problem because it doesn't have any physics to it. It just has you use the ideas of kinetic energy. It says, a father racing his son has half the kinetic energy of the sun. Okay, so we've got 1/2 m dad v dad squared. That's the kinetic energy of the dad. And he has 1/2 the kinetic energy of the sun. So that's m sun v sun. Oops, I have to have a 1/2 in there to keep this consistent. 1/2 times 1/2 m v sun squared. Okay, so the dad has 1/2 of the kinetic energy of his son. Kinetic energy of the dad, kinetic energy of the son. The father speeds up by 1 meter per second and then has the same kinetic energy as the son. Okay, so if I go 1/2 m dad, and now I'm going to take that original v dad and add 1 meter per second. Now, instead of having to have this 1/2, I am simply going to have the same mass of the sun, speed of the sun, squared. Now it asks, what are the original speeds of the father and the son? Pause. All right. Oops. Okay, so just looking at this from a math perspective, I've got a couple of more unknowns than I have than I have variables. I don't know the mass of the dad, the v of the dad, mass of the son, v of the son. So you'd think, oh golly, it looks to me like I'm going to need 4 equations, 4 unknowns. But let's see, maybe we can do something good. Let's take the top row and multiply both of them by 2. Okay? So this is just going to be m dad v dad, and over here, oh, well, heck, look at this. This on the top is the same as that on the bottom. And so let's go ahead and take minus of both sides here. I can multiply both sides by -1, and then I'm going to add our 2 equations. And it looks to me like I have 0 equals 1/2 m dad v dad plus 1 meter per second squared minus m dad v dad squared. All right, nice. Now look at how nicely this worked. Because I have a 0, I can divide 0 by mass of dad, and it's still going to work. And so let's multiply this by 2 and divide by mass of dad, and it's going to give me v of dad plus 1 minus, and remember I multiplied by 2, minus 2 v dad squared equals 0. Oh, whew. I got rid of mass of dad. So, and this has to have a squared on it, so I'm going to have v dad squared plus 2v dad plus 1 minus 2v dad squared equals 0. Okay, so then you can go ahead and get v dad squared minus v dad squared plus 2 v dad plus 1 equals 0. And at this point, you can go ahead and either factor it or use your quadratic equation to find out what v dad is. Once you know v dad, you can stick it back in, and it should be possible then to go ahead and find your v sun. Okay, so I'll leave that with you. That is not much of a physics problem. It's more just a little bit of a math problem. Now, why the heck would I do this? Well, the idea is that we're going to reformulate our problems that we've been doing just by writing down free body diagrams and solving Newton's second law. We're going to try to do this in a simpler, slicker way. And how are we going to do it? Well, we're going to do it by talking about kinetic energies and changes in kinetic energies that are caused by putting energy into the system or taking energy out. And the amount of energy that we either put in or take out of the system is called the work. So let's see how we can get this. Let's say that we have a constantly accelerated object. And we know that v equals v naught plus 2ad. What is that? Well, that's the same as the equation v naught, I think the way that I have it on the equation sheet is probably v squared minus v naught squared equals 2a times x minus x naught. Okay, so that's the same equation. So that's part of our constant accelerated motion. Now, what am I going to do? Well, we know that accelerations are caused by forces. So, in this place of this acceleration, we're going to put A equals F over M. So this object has some mass, there's some force acting on it that's causing that acceleration. And so we're going to go ahead and write v squared minus v naught squared equals 2 times F over M. And then this is the distance that that force has been applied. Okay. Now let's just go ahead and multiply both sides by m, divide both sides by 2, and you get this out. You get that the kinetic energy final minus the kinetic energy initial equals the force that you applied times the distance over which that was applied. And we call that the work. Now, the only caveat to this is that this force times distance, we call it the work. That's the energy that you're putting into the system, or as we'll learn, you can also apply energy, a force and basically take kinetic energy out. So you can imagine if an object is coming towards you and you push on it, you can slow it down, so you're doing negative work on it in that case. But the force that matters is the force that's going to be in the direction of the motion. Okay, so let me go to the next slide. I have a little bit better illustration of this. So we call this statement that I've just told you, the kinetic energy after the network is done equals the kinetic energy before the network plus the amount of work that you're putting in. And just to make it clear, here's a nice example from your book where if you're pulling, for instance, a bead along a wire, only the component of the force that is actually along the direction that you're causing the acceleration is doing work. So it's if you're just pulling up and the wire is pulling back, you're not going to change the speed of the bead. So it's only the force that's in the direction that can change it that matters. So that's why we say the work is the force times the distance times the cosine of the theta between the force and the distance that it's gone. Another way to calculate this is if you have your force written as a vector. So for instance, let's say that it's in the xy plane, fx, fy, and you have your displacement written as a vector of x displacement, y displacement. You could write this as f dot d, and this is called a vector dot product, and it gives you the magnitude of f times the magnitude of d times the cosine of the angle between them. And the way that this is calculated is just by the x components multiplied by each other plus the y components, fy times y. So you keep the signs. So for instance, if fx was negative, you would keep that sign around, and it takes care of this convention. Okay, so you can choose to use that or not. Okay, so let's just do a quick practice problem with this. If we ignore friction effects, the amount of energy required to accelerate a car from rest to speed v is E. Okay, so if you have kinetic energy before the network and the kinetic energy after this would be 1/2 mv squared. The network that we would put in is E. Now, the question that they ask is, what additional amount of energy is required to accelerate the car to a speed 2v? Well, let's see. Our kinetic energy after the network is done would be 1/2 m 2v squared equals the kinetic energy before that network would be 1/2 mv squared plus the amount of work done. So they want us to find that. Okay, let's do it quick. So this would be 2 squared is 4. So this would be 4 divided by 2 would be 2 mv squared equals 1/2 mv squared plus w. So subtract off 1/2 mv squared from both sides, and you get 3 halves mv squared equals w. And notice that that is 3 times this. So 3e equals w. So the answer, now we got it. That's all right. But the moral of the story is to get up to a speed of v, you needed an energy E. To get up to a speed of 2v, you need an energy of 4e. So doubling that speed, you have to add in 3 more energy units than to get to just the first one. So increasing your energy or increasing your speed takes more work the faster you're going. Okay, so that's a sort of an interesting point. All right, so here's a practice homework problem for you guys. It says a coin slides over a frictionless plane and across an xy coordinate system from the origin to a point with xy coordinates 3, 4. So there's 3, there's 4. So your displacement is going to be 3, 4. Now everyone knows your 3, 4, 5 right triangle, so this distance has to be 5 meters. The force has a magnitude of 2 newtons and is directed at a counterclockwise angle of 100 degrees. So this angle is 100 degrees from the x-axis. And it asks how much work is done by the force on the coin during the displacement? Well, notice that you can't just use this formula directly because the force, we know this has a magnitude of 2 newtons, but you can't just go 2 newtons times 5 newtons times cosine of 100. Why? Because this is not the angle between these two vectors, it's the angle between this and the x-axis. So one way that you could do this is to find this angle here, let's call that angle 1, and then your phi would be 100 minus that angle 1, where angle 1, I guess one way that you could do it would be to go inverse tangent of 4 meters over 3 meters, so 4/3. And then find this, and then go ahead and use 2 times 5 times cosine of 100 minus that angle 1. So that'd be one way to do it. Another way to do it would be to go ahead and write your f as a vector as well, and then that would be f times cosine of 100, and then so not to be, this would be 2 meters, or 2 what did I put, this is 2 newtons. 2 newtons times cosine of 100, and then 2 newtons times sine of 100. Notice that this is going to be negative because it's pulling in the minus x direction. And if you took that dot product, you would take this times 3 plus this times 4. And would it have the right units? It would, because it would be newtons times meters. Newtons times meters gives you units of energy, which is joules. Okay, now I had intended to do more than this in this class period. However, in the live meeting of this section, we didn't get through any more than that, and so I'm going to cut it a little short. We'll come to this on Monday. All right. So basically, if you push in the direction of the motion, you do positive work. If you push opposite the direction of the motion, you do negative work. But we're going to go through this on Monday, and I'm going to leave it at that. So what are our lessons for today? We've got the kinetic energy of an object depends on 1/2 mv squared. The kinetic energy of an object may be changed by doing work on it. And on Monday, we're going to talk about how work can be positive or negative. It's positive if you're putting energy in, if you're causing the speed to increase. It's negative if you're pushing opposite the direction of motion, causing the speed to decrease. But let's leave that for Monday. What I would recommend is I have posted your assignment. This assignment is not due this coming Monday. It's due 1 week from Monday. And so because it covers 4 class periods, it's quite a long assignment. And if you leave it to next weekend, you're probably not going to get it done. It's too long. So what I would recommend is this weekend, try to do the first half page of it or so. Try to knock that first as much of the first page as you can out, and it's approximately 6 problems for every class period. So if you do 6 problems a period, you'll get it done. It's not going to be too hard. But if you leave it all for next weekend, it's probably going to be too long. So just be aware. All right. So thank you for watching the video. Welcome back to Centenary. I don't know. Anyway, weird week, but I hope to see you all on Monday.